For our last few mini lectures of the semester, we are going to be talking about modern physics. So far, everything we've really been talking about falls under the realm of classical physics. Modern physics is a branch of physics that began to be developed in the early 20th century. And under the umbrella of modern physics, we have things like special relativity and quantum mechanics, for example. These were new branches of physics that changed our entire paradigm understanding of how we approached different types of problems in our universe. And when we think about classical mechanics or classical physics, which is what we've really been studying for the entire physics course until now, covers just about anything that's larger in size than 10 to the minus 9 meters and that is moving at a speed much, much less than the speed of light. Whenever we take these objects and start moving them faster and faster and moving them such that their speeds approach the speed of light, that's when we start thinking about relativity. Now, which is going to be the topic of this mini lecture. When we start thinking about things on the smallest scales in our universe, things near or less to 10 to the minus 9 meters, when we get all the way down to the scales of individual electrons and protons, for example, that's whenever we start thinking about quantum mechanics. And our next few mini lectures are going to be covering relativity and quantum mechanics. This mini lecture is going to be all about relativity. What do I mean by relativity? Relativity is all about your frame of reference. And here I have an example. Your frame of reference is different for the things moving with you inside the bus and the things moving outside the bus relative to you. Your frame of reference is everything that's moving with you inside the bus. And so you're sitting there inside the bus, the person sitting next to you inside the bus. You do not move relative to the person who's next to you because you're both in the bus traveling at the same speed. But everything outside the bus is a different frame of reference. For you inside the bus, it doesn't look like the things around you inside the bus are moving, but everything outside, the trees outside, the houses outside, you're zipping past them and they appear to be moving relative to you. That's relativity. Classical physics has a few problems, especially whenever you think about things that are moving very quickly. It's possible to accelerate an electron to a speed of very, very close to the speed of light. You set up a potential of several million volts, and then because of that potential difference, you can accelerate that electron, okay? And you can get it moving at very, very close to the speed of light, but anything with mass can never exceed moving past the speed of light, or anything with mass actually can never actually move at the speed of light, but it can approach the speed of light. So in Newtonian physics, or that's our classical physics representation, increasing the potential difference by a factor of 4 will result in an increase of the kinetic energy by a factor of 4, which should double the speed of our electron to 1.98 c, 1.98 times the speed of light. So why? Well, we saw earlier in the semester how changing the potential difference that an electron moves through will also change its speed, will increase its speed or decrease its speed depending on how you change that potential difference. Kinetic energy of a classical electron is 1/2 mv squared. So the kinetic energy is proportional to the speed squared. If you increase the kinetic energy by 4, you're going to change the speed by a factor of 2, as you've got k is equal to 1/2 mv squared. So increasing our kinetic energy by a factor of 4, we really bump up that potential difference by a factor of 4. We could double the speed of our electron to twice that, the speed of light. under classical physics. But experiments show that the speed of any particle that has mass always remains less than the speed of light, no matter what. Our universe has a speed limit. That speed limit is the speed of light. Sometimes we represent it as c, the letter c, which we'll be doing here. C is 3 times 10 to the 8 meters per second. So because there is a speed limit to the universe, there is a problem with using classical mechanics whenever you approach things that are moving very close to the speed of light. Classical physics also has another problem, and it all has to do with how we add up velocities, relative velocities. So imagine you are a train conductor. Here you are in the engine of a train. Your train is moving forward with a speed of v, but you are moving with the train engine. And we're thinking about the light coming from the headlight of your train. You're moving along with your train. You're going to see the light from the headlight of your train move away from you in front of you at a speed of 3 times 10 to the 8 meters per second. But let's say that there is a stationary observer out here who is watching that train come toward them, and they see the headlight of the train. So according to classical physics, a stationary observer here should see the light from the train traveling toward them at a speed of the speed of the train plus the speed of light, 3 times 10 to the 8 meters per second. Because we know that light is traveling with some speed, c, but that headlight is attached to the train, so that headlight itself is also moving at some speed, v. So if you add those together, under classical physics, you should see the speed of light coming from that train headlight as traveling faster than 3 times 10 to the 8 meters per second. But we know that nothing can travel faster than the speed of light. So we have to come up with some way to explain the fact that things are moving, but things can never travel faster than 3 times 10 to the 8 meters per second. Special relativity was created to reconcile some of the difficulties with classical physics, especially for objects moving close to the speed of light. Special relativity is all about relating measurements in different frames of reference. So again, here's our image from earlier. We've got 2 different frames of reference. We've got the frame here, someone sitting inside the bus, moving with the bus. And then we have the frame of reference outside the bus. So measurements that you make in the frame of reference in the bus and measurements that someone makes in the frame of reference outside the bus of the same event occurring at the same time, those measurements could be different and will be different. In 1905, Albert Einstein, at the very young age of 26, proposed a theory to reconcile the contradiction between the classical addition law for velocities, which is what we were just talking about, and the fact that the speed of light is the same for all observers. This was Einstein's theory of special relativity. And the theory of special relativity applies to unaccelerated motion. That means motion at constant speeds. Einstein also proposed the theory of general relativity, which applies to accelerated motion and gravity. But here we're only going to talk about Einstein's theory of special relativity. If you want to learn about general relativity, which also has to do with black holes, you can take my astronomy class. Special relativity is based on 2 postulates. The first postulate is called the principle of relativity. All the laws of physics are the same in all inertial frames. The laws of physics are the same for everybody, no matter how you're moving. What do I mean by an inertial frame? An inertial frame of reference is a frame of reference in which a body at rest remains at rest and a body in motion moves at a constant speed in a straight line. When I think about inertial frames, though, I tend to think more about like imagining an event or a situation, and you place a little box or room around it. The inertial frame for me is me sitting right here in this room in my chair, okay, at this very moment. An inertial frame for me would be if I got into my car and started driving, I am in the inertial frame of my car, the inside of my car. An inertial frame for someone moving in a spacecraft, that person inside the spacecraft is in the inertial frame of that spacecraft. The second postulate of special relativity is the constancy of the speed of light. The speed of light in a vacuum is constant and it's independent of the motion of the observer or the source. So no matter what, the speed of light is a fixed quantity, no matter your inertial frame. So what are some consequences of special relativity? There are some weird and unusual consequences for this fact that all laws of physics are the same, no matter what reference frame, and that the speed of light is fixed. One of those is called simultaneity. Two events that are simultaneous in one reference frame are in general not simultaneous in a second reference frame moving relative to the first. So there's no guarantee that something that happens in my reference frame happens at the same time as it happens in your reference frame. Simultaneity depends on the state of motion of the observer and is therefore not an absolute concept. That's a little bit weird. And I see that actually I made a lot of spelling errors in these slides today, sorry. Another consequence of special relativity is time dilation. In time dilation, time passes slower for an observer who is moving relative to another. So sometimes we say this as moving clocks run slow. In my frame of reference, I'm going to see that event take place over some time period. But for you, because you are moving very close to the speed of light, you're going to see that event unfold over a much longer time. It's going to take longer in your frame of reference for that same event to occur. So that's what this means here. And then length contraction is another consequence of special relativity. The length of an object measured in a reference frame that is moving with respect to the object is always less than the proper length. The proper length is the length of the object as measured by an observer at rest relative to the object. So I'm measuring something here in my reference frame to be some length, and you in your reference frame, you're traveling at very close to the speed of light. You're going to see that same object as being shorter compared to what I measured it to be. So those are all consequences of special relativity. With time dilation and length contraction come some equations, but we're going to take a look at those equations here. Time passes slower for an observer who is moving relative to another. That's our idea of time dilation. And we're going to identify a few terms here. We're going to call proper time delta t sub naught the time interval that's measured by an observer at rest relative to the event that's being observed. So we could say that this observer is in the inertial frame of the event that's occurring. And then we have another time interval, delta t. And this is the time interval measured by an observer for that same event who is not in the inertial frame of the event. So the time interval delta t is equal to gamma times the time interval delta t naught, which was our proper time. This term here, gamma is equal to 1 over the square root of 1 minus v squared over c squared, where v here is the speed of the observer that's moving relative to our stationary frame where the event is occurring. Here we have an example of time dilation as it's related to a fundamental particle that we call a muon. So this muon here is traveling with some speed v. This muon, let's say, has a watch. It has a clock. Now, even though the muon is traveling with some speed v, in the muon's frame of reference with its clock that it has on there, it's measuring time. And the time that it is measuring in its frame of reference, we're going to call that, for the muon, its proper time. We're going to call that delta t sub naught. Okay. Now let's say that this muon, according to its clock, its watch, moving with it, has a lifetime of 1 hour. Okay. And then we have this person over here who is stationary on the Earth. They're not moving. They're in a different reference frame compared to the muon. This person will see the lifetime of that muon be equal to gamma times the proper time or the lifetime of the muon as measured from the muon's frame of reference. So this person here will see that from their frame of reference, the muon is actually going to live a longer time in their frame of reference compared to the muon's frame of reference. And that all has to do with our differences of reference frames and the fact that this muon may be traveling very close to the speed of light. So this quantity gamma here is a quantity that changes as you approach the speed of light. This graph here shows us how gamma changes as the velocity changes. So as you approach closer and closer and closer to the speed of light here, gamma is going to get bigger and bigger and bigger. So gamma is on the vertical axis, velocity is on the horizontal axis. As this v here increases from 0 and approaches the speed of light, this quantity gamma gets larger and larger and larger and larger. So that difference between the proper time and the time measured by someone not in the reference frame of the event that's unfolding, that time difference is going to get greater and greater and greater and greater the closer that object is moving to the speed of light. Length contraction refers to how the length of an object changes when you travel close to the speed of light. The length of an object measured in a reference frame that is moving with respect to the object is always less than the proper length. So if you are moving at some speed, that especially as you approach the speed of light, you will measure the length of an object to be shorter than what it actually is. That's length contraction. Now we're going to call proper length L sub naught the length of the object as measured by an observer at rest to the object. So for me, the proper length would be me taking, I've got my phone here, measuring the length of my phone right here. I am not moving with respect to the phone, so the proper length of this object is the length that I measure it to be here, me not moving with respect to it. And then L is the length of an object measured in a reference frame that is moving with respect to the object. So I'm here stationary, and let's say that you are moving close to the speed of light and you're looking at my phone. The length that you measure, L, is going to be different than the length that I measured, L sub naught. And the length that you measure, because you're moving close to the speed of light, is going to be shorter than what I measured. And so we can represent how those two lengths are related with this equation here. So the length of the object measured in the moving frame of reference equals the proper length of my object divided by gamma. So this time we're dividing by gamma instead of multiplying by gamma like we do with time dilation. Here's an example of length contraction. I have the Earth and Alpha Centauri, which is the closest star to us beyond the sun. And from an earthbound observer, they measure the proper distance between the Earth and Alpha Centauri. That's going to be L sub naught here. And then we have somebody in this spacecraft. There's an astronaut inside this spacecraft. this astronaut is going to be inside the spacecraft and they're going to travel at close to the speed of light. Okay, and as this person is traveling, they are going to measure this length between the Earth and Alpha Centauri to be shorter than the length that the stationary observer measures it to be on the Earth. So that is our idea of a length contraction.